The 2D polar coordinates are r and phi. R refers to the distance from the origin, the radial distance from the origin, and phi is the angle measured counterclockwise starting from the x-axis, which is taken as phi equals 0. So phi increases in the counterclockwise direction, whereas r increases radially outward. In this case, our lines of constant r are circles, and the lines of constant phi are straight lines passing through the origin at fixed angles. There are unit vectors in this coordinate system as well, r hat and phi hat, but unlike I hat, j hat, and k hat, the directions of r hat and phi hat change as we move around. So for example, here, direction of r hat is like this, but over here, direction of r hat is like this, and over here, it is like this. However, it is still a unit vector, so its magnitude, that is, its length, is 1. Similarly, phi hat also changes. Phi hat is tangent to these circles. Phi hat over here points like this. Over here, it's tangent and points like this. And say we were over here, phi hat would point like this. Though again, the length doesn't change, it's a unit vector and has a length of 1. In these coordinates, our position vector is simply the magnitude r times the unit vector r hat. Where is the information about phi? Well, r hat is actually a function of phi, which makes sense because the direction of r hat changes as phi changes. Due to this, finding the infinitesimal change in r is now a little bit more complicated. It becomes dr times r hat plus r times d of r hat. So to proceed further, we will need to figure out what d of r hat is. So, in general, when you have f being a function of two independent variables x and y, then df, the change in f, is given by the partial derivative of f with respect to x holding y constant times dx plus the partial derivative of f with respect to y holding x constant times dy. In other words, the total change in f is a combination of the change in f due to x plus the change in f due to y. Similarly, the change in r hat, which is a function of phi and r, will be partial r hat partial r times dr, this partial derivative when phi is being held constant, plus partial r hat partial phi with r being held constant times d phi. Now we can already see pictorially that r hat does not depend on r. For example, if I look at r hat here, it points like this. If I look at r hat here, it still points in the same direction, and we know it has the same length. So this term will go to 0. That leaves us with how r hat depends on phi. we know that when finding a derivative, for example, partial f partial y, what we are doing is taking the limit as h tends to 0 of f of x y plus h minus f of x comma y divided by h. In other words, we leave x alone, holding it constant, and allow y to vary by a small amount h. We look at this difference and take the ratio over h and take the limit as h tends to 0. We are going to follow a similar procedure over here, focusing on how the r hat vector changes as the angle phi changes. So we are going to zoom in a little on this diagram.
So let's say we have two lines.
The angle between them is d phi. At this point, r hat points like so, and at this point, r hat points like this. What we want to do is look at how r hat has changed. So we take the difference between these two vectors. And to do that, we first move this vector over here. So without changing its direction, we move it down over here. And we look at the difference between these two vectors. So blowing that up a little, we have r hat, you could say initial over here, and then we have r hat final over here. And the difference between them, r hat final minus r hat initial, points like that. And again, the angle between them is a small angle d phi. Now, for an infinitesimal angle d phi, this starts to resemble a sector of a circle, in which case this vector that we want is related to this arc length. We can see from this diagram that the direction of this difference vector over here, let's call that delta r hat, is in the limit as d phi goes to 0, this vector is perpendicular to r hat. And so the direction of delta r hat is going to be in the phi hat direction. But what about its magnitude? For that, we pursue this similarity with a sector, and we say that, oh, well, the arc length over here, if this is an angle d phi, and this is some radius r, well, then this tiny arc length ds will be r times d phi. So what that tells us is that the magnitude of delta r hat is going to be the magnitude of the radius, which is just r hat, times d phi. But we know that the magnitude of r hat is 1, so this is just d phi. And we have established that the direction of delta r hat is in the phi hat direction. So in fact, what we get is that dr hat is equal to d phi times phi hat. Since there is no r dependence, we can in fact write this as partial r hat partial phi is equal to phi hat. And plugging that back in over here, again we simply get the relation dr hat is equal to phi hat times d phi. So returning to the infinitesimal change in the position vector, we said that dr vector would be change in the r coordinate times r hat plus r times the change in the unit vector r hat. Using the result we just got, we can replace dr hat with phi hat times d phi. So we obtain dr vector is equal to dr times r hat plus r d phi times phi hat. Let's think about if this makes sense.
Remember our coordinate system is a bunch of circles and straight lines.
What this is telling us is that, oh, if I want to move from here to here, I move a certain distance dr out in the radial direction, and then I move in the phi hat direction a distance of r d phi. So yes, the combination of those two motions takes me from here to here. Once we have this, we can now talk about the velocity. dr dt or in the dot notation, this can also be written as v radial times r hat plus v tangential times phi hat. This is our velocity vector in 2D polar coordinates. If we want to go on to acceleration, we will need to take the derivative of this, and we can see that that would be r double dot times r hat plus r dot times r hat dot plus r dot times phi dot times phi hat plus r times phi double dot times phi hat plus r phi dot times phi hat dot. All I've done is apply the product rule to this expression over here. We know what to do with r hat dot, but we see that we also have a phi hat dot over here. So again, let's look at a similar picture. We're looking at a little slice, and we're trying to see how phi hat changes. So if we only move out radially, again we see that there's no real change in phi hat. The direction and the magnitude both stay the same. However, if we proceed along the phi direction, we see that the direction of the phi hat vector does change. Phi hat over here does not point in the same direction as phi hat over here. So again, we look at the difference between the two vectors. So we have our original phi hat pointing like this. Let me make that a bit longer. And then the new phi hat pointing like this, and the difference between them pointing like this. And so we see that delta phi hat points inward along the negative r hat direction. As for the magnitude, we find once again that this magnitude will be related to an arc length picture. And so we have that d phi hat is equal to magnitude of phi hat times d phi. So that's the radius times the infinitesimal angle here. And the direction is in the negative r hat direction. And so that simplifies to d phi hat is equal to minus d phi r hat. So with this relation, along with our previously derived d r hat equals d phi times phi hat, we can now go to the acceleration. R double dot times r hat plus r dot times r hat dot. So we can see that r hat dot, which is d r hat dt, is just going to be d phi dt times phi hat, which is phi dot times phi hat. So we plug that in, phi dot times phi hat. We have another term which is actually identical, so then here we pick up a phi double dot term, and finally we have the phi hat dot term. So we have r phi dot and then phi hat dot, which we can see from here will be minus r hat times phi dot. So let's collect all the r hat terms together, all the phi hat terms together. For r hat, we have r double dot. Any other r hat terms? Yes, here. Minus r phi dot squared. And for phi hat, we see these three terms. These two combine into 2r dot phi dot, and then we also have this term over here. Now, of course, this isn't particularly illuminating, but we can check it by looking at certain special cases. So, for example, if we look at motion in a circle, that is motion with constant r, well then, since r is not changing, r dot goes away, r double dot goes away, and so we have if r is equal to r naught constant, then a is equal to minus r phi dot squared r hat. Then over here we have plus r phi double dot phi hat. But if we recognize phi as the angle, phi dot as angular velocity, and phi double dot as angular acceleration, then this just becomes minus omega squared r hat plus alpha r phi hat. So this is in fact the centripetal acceleration or the radial acceleration plus the tangential acceleration. To complete our comparison with the Cartesian coordinate system, we look at the infinitesimal area dA. So now that would be this little portion, and we see that for a small angle this little almost trapezoidal shape has, well, for a small enough angle it reduces to a rectangle, has this side with the length of dr and this side with the length of r d phi. And so we get that dA is equal to r d phi dr. Since this is 2D, we will not consider any volume element. Later, when we consider the extension of the polar coordinates into either cylindrical or spherical coordinates, we can talk about volume elements there. All right, so finally, we would like to know how to convert between our Cartesian coordinates and polar coordinates. Well, we have the relations x is equal to r cos phi, y is equal to r sine phi, and if we would like the reverse arrangement, we have r is equal to the square root of x squared plus y squared, and phi is equal to arctan y over x. Alright, well, that takes care of the coordinates themselves, but what about the unit vectors, r hat and phi hat? Can we express them in terms of I hat, j hat, and k hat? As it turns out, yes, we can. To do so, we realize that r hat points in the direction of increasing r. This sounds obvious, but it has an interesting implication. It implies that r hat will be proportional to this. This is the partial derivative of the position vector with respect to r. All right, let's evaluate. We can always write the position vector in terms of x, y, and z, so this becomes of course, this is because I hat, j hat, and k hat do not depend on r. That's why we treat them as constants. All right, well, partial x, partial r is just cosine phi. Partial y, partial r is just sine phi. And in this case, there is no z coordinate. So we are left with this is cosine phi I hat plus sine phi j hat. And this will be proportional to the r hat vector. Well, let's check what its magnitude is. If we take the magnitude, we get cosine squared phi plus sine squared phi, which is equal to 1. So it is already a unit vector, and in fact, this is our expression for r hat in terms of I hat and j hat. Let's try this again. How do we find phi hat? Well, phi hat will again be proportional to how the position vector changes as phi changes. That is, it points in the direction of increasing phi. Again, I hat and j hat do not depend on phi, so we have this simple expression. Partial x partial phi is going to give us minus r sine phi. Partial y partial phi will give us plus r cosine phi. Is this our vector phi hat? Not quite. If we take the magnitude what we end up with is r squared sine squared phi plus r squared cosine squared phi, square root of that, which is r. So this is not quite a unit vector, it has a magnitude of r. However, we can use this to construct a unit vector by simply dividing this by its magnitude. And so we get phi hat is equal to 1 over r times this, or in other words, phi hat is minus sine phi I hat plus cosine phi j hat. We can check if these expressions make sense by checking a few simple cases. When phi is equal to 0, we see that cosine of 0 is 1, sine of 0 is 0, and so r hat points in the I hat direction, which makes sense. R hat does point in the I hat direction when phi is equal to 0. Similarly, when phi is equal to 0, phi hat will point in the positive j hat direction. Yes, that is correct. What about over here when phi is equal to pi over 2? When phi is equal to pi over 2, r hat will point in the positive j hat direction, yes. And phi hat will point in the negative I hat direction. Yes, that does make sense. So this is how we obtain expressions for r hat and phi hat. Now that we have these expressions, of course, we could find it much easier to get dr hat, at least in terms of I and j. So we would have dr hat is equal to d cosine phi I hat plus d sine phi j hat, but d of cosine phi is just negative sine phi d phi I hat. D of sine phi is positive cosine phi d phi j hat. But this turns out to be d phi times phi hat. And similarly, we can get an expression for d phi hat. You should practice this technique with the other coordinate systems that we will look at, the cylindrical and spherical coordinate systems. And you should also practice expressing I hat and j hat in terms of r hat and phi hat.